Well, thank you very much, and I'd like to start by thanking Ali, of course, and Sherman for the invitation coming here. And there are two reasons I want to mention in the very beginning. The first is that when Sherman talked to me, I told him immediately, well, I think that part of the future of quantum computing is in the material science. There's no question for many of us. So this is an excellent opportunity for me to meet some of the people that are in the field. And the second is that he was very obvious. It was obvious that I could say anything. He said, okay, if you can review a little bit what's going on, no need to be politically correct. Wow, that's a pleasure, no? As director of CQT, I always have to be careful, so today, no. I'm also directing the center, the new center in Abu Dhabi, the TII. There is a quantum research center, which only has 2 years, but in 2 years we already have a small quantum computer. So the barrier to make a quantum computer is not that high. Okay? And finally, I produce a startup in Barcelona, where we are also working superconducting qubits. So does it work? Oh, no. The first comment I want to do is that quantum computing is coming, indeed, no question about that, but it's not coming at the pace of the hype in the media. It's coming definitely at the pace of science. And that requires a lot of patience to deal with the media, and in particular with the people that provide the money, okay? There is a misconception that we can go very, very fast in quantum computing, and this is certainly not true. What I will be doing today is to talk a little bit about the landscape of quantum computing, figures of merit, how a quantum computer is good or not, and then go back to a little bit of theory, talking about the Hilbert space, these ideas that now we have about tensor networks, variational quantum algorithms, and the new focus on sustainable computing. So the landscape, just in one transparency, things which are going on. Well, there are like 3 main ideas. One is universal quantum computation, the other is quantum simulators, and the third one is quantum annealers. Let me make it very clear. The first, you want to do any computation. You want to do Shor's algorithm and break cybersecurity. That's a quantum computer, a universal quantum computer. And ideas, we have qubits based on transmons, which are superconducting currents in ions, in solid state, spins in NV centers, in cavity, in photons. At CQT, we have actually the 6 platforms, so we work with all of them. Quantum simulators is something different. You don't have universal gates, but you have enough control of matter to simulate other quantum systems. And now, in particular, in the last couple of years, there has been an enormous progress in cold neutral gases and also in integrated photonics. So there, the spirit, actually, one of them is to simulate condensed matter systems and also materials. And the third are quantum annealers. And they are both based on more simple qubits like transmons, also on the more a different set, which is flux qubits, even fluxonium. Okay? So on the first column, the companies are, there are a lot of companies working on that, and those are, you know very well, Google, IBM, Rigetti, IonQ, all of them. Let me just highlight a few of the recent news for you. IonQ just released now a 23 qubit machine where they have interaction with all order of magnitude of the errors, 0.01% per gate, which is really remarkable. And with gates which are not two-body, they have many-body gates, okay? So that's the interactions of nature. Let me mention IQM. IQM will be releasing the 25 qubit machine in January. This is in Finland. Quantware, they are doing something very special. Because it's so difficult to characterize a chip, They are producing, fabricating chips, and selling them without characterization. It's up to you if you believe this will be a good chip or not. So at present, Quantware, they are selling 5 and 21 qubits, and they will be selling 64 qubits at prices which are really not that high, so that you can work with them. Let me mention, for instance, Colquanta is trying to sell Einstein machine, Albert machine, that in principle automatically will take you to nanokelvins. Okay? They have an emphasis in sensing too. Or Xanadu just released a photonic chip for boson sampling of more than 200 waveguides. And on the D-Wave, as you know, they have gone a little bit crazy to 5,000 qubits. And I will mention our initiative. So Kilimanjaro is leading an initiative in Europe to make a quantum annealer which is coherent. So the emphasis is coherence. So not like D-Wave, not the number of qubits, but coherence. To this, you have to add all the labs. There are many universities which are doing a fantastic job. But in particular, I want to mention HPC centers, so high-performance computing centers. You may have read the news that a month ago, the European Union, through the HPC initiatives, they issued, it is called HPC Quantum Computer and Simulation, CSC, Quantum Computer, QCS. They fund now 6 quantum computers in Europe, which are sitting at supercomputing centers. So the idea is that quantum computation is thought as coming to the places where supercomputation is. Okay? For why there are still so many platforms? Well, because there is no winner of what the best quantum computer platform is. And why there is a competition? Because there is a clash. Okay, it's an obvious clash, but many people don't see it. The clash is that on one hand, you need to protect your qubit against decoherence. So you have to protect it. But if you protect it, then it's very difficult to interact. If you have a qubit that interacts easily, then it's very difficult to keep it coherent. Okay, so this is the clash. Who is good to maintain the coherence? A photon. Okay? But then, you know, QED tell us that photons interact with alpha over pi divided to the 4 power, plus extra factors that makes negligible. So you need matter. And then you have to interact through matter. And then it's probabilistic sometimes. So it's extremely difficult to get something. Who is trying to do that? Psi-quantum. On the other hand, transphons can interact, but then they immediately, you get decoherence, okay? And this is the fight that we are in the middle of. Ions are in between. Ions have the privilege. The qubits are there. Nature gives you qubits for free. You simply pick one, and that's a qubit. An ion is a qubit. You don't have to do anything. Now, you have to keep it there. So the new idea is that people have levitating ions on chips, and this is the way now we manipulate them, okay? So we go from traps in 3D to levitating ions of a 2D chip. All this is going on, but from the point of view of business, the companies that are doing very well, extremely well, are those related to enabling technologies. So, as you know, I give you an example of blue force in cryogenics. Well, I cannot remember the exact number, but I think last year they sold 200 dilution fridges. So this is really spectacular. Fast electronics is moving very, very, very fast with all these, the old and the new companies. So you have the old, but you also have Q-blocks, quantum machines, and they are all trying to get fantastic control at the nanosecond scale of the electronics. Then you have cables, superconducting cables like Delft circuits and blue force also, quantum amplifiers, all the pieces which are needed, and even the control software is suffering a transformation. So you have companies like Orange Computing, Ketma, Horizon, Classic, all of them want to achieve a much better control of our physical devices through software. Okay? There is an ongoing big expansion of the use of FPGAs because it's needed, and many labs, little by little, they are working like integrators rather than developing the software. So the example is that now you can buy almost everything and try to put it together, including the chips. Okay? But it would be unfair to say that because quantum computing is coming, there isn't efforts on the classical world. So actually, in the last couple of years, the progress of classical computing has been astonishing. The first idea is that people have been focusing on what is the best way to simulate states so that you can mimic a quantum computer. We have been working a lot on simulating quantum mechanics, but typically we did that with Monte Carlo or exact state simulations. The push now, enormous push, goes in the direction of tensor networks. And I will mention lately what is the central idea of a tensor network so that you see why classical computers are getting so good nowadays. There is this new idea of quantum-inspired algorithms. So those are classical algorithms, but the logic they follow is suggested by quantum mechanics. An example for that is the solution of linear systems, that there is a quantum algorithm called HHL. And what you do is now you program the quantum algorithm, you simulate it. It turns out to be an excellent idea to solve these kind of systems. And recently, as last week, people have discovered that tensor networks, if you can represent your data with a tensor network, the Fourier transform, the standard Fourier transform, is extremely efficient. So if you codify the data as a tensor network, the Fourier transform is fantastically fast. And you have an advantage over any classical Fourier transform. And people have even been building classical machines which are quantum inspired. And you have machines like NVIDIA with the quantum. So what is the idea? That given that the operations you do for quantum are related to the manipulation of tensors, they are optimizing the flow of data between the units of computation. Or Atos has created a machine, Fujitsu has created a machine. Fujitsu has created an annealer, is simulating the annealing process on the classical hardware. And the middleware, something that very few people mention. In order to have a quantum device and a high-level algorithm, you have to connect them. And this is what people call a full stack. Now, the full stack is non-trivial, and there are not that many. You have Qiskit, they are all proprietary in the sense that the language may be open source, but the hardcore, all the parts of these are proprietary. Cirque, Kulax, Forest, Penny Lane. A common language, which is OpenQuasm, to talk to the computers in the very end. And you have to provide everything. You have to provide cloud access, you have to provide applications, you have to provide scheduler, you have to do the calibration, automatize, you have to do transpiler, you have to go to the native interactions of the system. Quite an effort to do all that. What we are doing, and this is what I'm trying to show over there, is there a pointer? The first one, okay. Uh-oh. Yeah, not very intense. What we are doing under the name of Kibo, it's an open source initiative that wants to be a sort of Linux for quantum devices. What we are doing now is backends of simulations. We have already multi-GPU, multi-node to go to supercomputers, tensor networks, and we deal with the lab with transmons and ions. And now we are building the drivers to the machines so that actually Kibo at the top level, you can give instructions and they understand the equipment that you may have in your lab. A lot of the emphasis, as I said, is being pushed to FPGAs. So why we need FPGAs? Because typically FPGAs are used, for instance, for high-frequency trading in the stock market, because you need to get the news and take an action very fast. The limit nowadays is of the order of 60 nanoseconds to take an action in the market. In artificial intelligence, you use them because you want extreme power, adaptive extreme power. Ours is different because what we need is a control at the natural scales of the physics, which is nanoseconds. So actually, we have really to work on the nanosecond scale with our electronics. We cannot use electronics of microseconds. We have to go to nanoseconds. That's why FPGAs are now dominating the landscape. And finally, I should mention that there is a big issue about how they call now segmentation, no? Instead of globalization, segmentation. To give you examples, we have gone through clearance procedures to buy equipment from Europe, okay? We have suffered exportation bans both in Singapore and in Abu Dhabi. Pieces of equipment which are not sold. And definitely there is an issue of talent. Immediately as you educate somebody, puff, yeah, you lose him. In general, all countries are conscious of the idea that they have to develop their own strategy. And you may be familiar with many of the national plans that are going around. All of them are very similar. All of them talk about the three pillars: quantum computing and simulation, quantum communication and cybersecurity, quantum sensing and metrology. And now many more people talk about enabling technologies and obviously basic science. Because without basic science, you will miss the big progress which is coming. Given that all this is similar for every country, you see that what makes the difference really is the speed. So what we are seeing everywhere is that those countries with a lot of bureaucracy are lagging behind, literally. Okay, literally lagging behind. European Union flagship is lagging behind. Why? Because it's an amazing amount of bureaucracy. You see actually the opposite, that the startups are doing well because they have less bureaucracy. I'm the direct witness of different countries because in the European Union, I'm involved in 3 places, and by far the progress is related to the lack of bureaucracy. Okay? Of course, of funding. You need funding, but you need agility. Okay? Okay, this was a little bit of just to say what's going on in the planet. Okay? And what I would like to do now is just to go back to, little by little, to theory, to tell you a few of the things which are going on, okay? It's my personal choice. It's not that this is the most relevant thing going on. So I will, I forgot. I would like to mention just that the figures of merit that people are using is a mess. We all agree that this has to be cleared. So when you go to marketing, news. Actually, I said here the figure of merit is the number of qubits. Any announcement says that many qubits. Well, the figure of merit is money. The first thing they say is how much money. Okay, they got. But the number of qubits is typically used as a figure of merit. Then, if the communication has a more solid background, they start to explain that there is a coherence, and they talk about coherence time. And they talk also about get fidelity. But as a matter of fact, you never see news that tell you about the depth that you can support in your chips, the fidelity of the circuit, not of the gates, or the expressibility you have, or the entanglement support, or many other names that we are using constantly in science, they never make it into the news. Just to give an example, I know it's an obvious thing, but let me do it. If the number of qubits is everything, well, you know, and there are claims now, as you may know, of quantum computers with more than 100 qubits. Well, then you can factor. And Shor's algorithm only needs 2n plus 3 qubits. So you can factor if you have such a computer. And with this number of qubits, you should be able to factor a number of this size. As of last year, the largest number we have factored is 21. So what's the meaning of the figure of merit of number of qubits? Is really irrelevant, okay? And I mentioned a few problems, depth, circuit fidelity. Let me give you an example. I go to depth. This is a state, quantum state, which is called absolute maximally entangled. It's a state that has a peculiar thing, that whatever partition you make, you have maximal entropy. And you can make a circuit for it. Okay, so we have a quantum computer. Let's check it. Let's do it. And you do it, and when you look at the detail, when you put it in a real quantum computer, this is a real example, okay? This is one of the quantum computers of IBM. Well, that circuit is implemented like this. And then on top, this has to be translated to the native gates of the circuit. So you see, when you count the depth, which is how many things you can do in parallel, so here you have formally 1, 2, 3, 4, 5, 6 of depth. As a matter of fact, it's 17. And as a matter of real fact, when you do the native gates, is even worse, okay? So how much depth you can get? Well, it's related to your T2 versus the gate time. And in some cases, you go up to 200 nanoseconds, and you have T2s of microseconds. So formally, you think you can do 1,000. In practice, it's less. So actually, we are dealing nowadays with depths of 20 to 30, no more than that. And with that, we can do very, very, very little. Okay? That's the reason why practically we don't have any good result. But to solve that, you have to go to the real physics. You have to understand why this is the limitation. This is an example of the circuit fidelity. Again, I propose a challenge. You tell me, I have a quantum computer. I say, I don't believe you. I don't believe you. So give me access, and remotely, what I do is that I run Bell inequalities in your computer. I see if this is a quantum computer. So the generalization of Bell inequalities are Bell inequalities for multipartite systems. So this is an example of the 3 Mervin inequality, 4 and 5. And you can run them. And this is the result. No? You have 2 local realism, 4 and 4 for 3, 4, and 5 qubits. The limit in quantum mechanics, if the state is perfect, would be 4, 8 to the square root of 2 or 16. And when you do the experiment, the numbers you get are those. Okay. So as you can see, for 2 and 3 qubits, you do violate Bell inequalities. For 4, it gets tough. For 5, essentially, you are not violating Bell inequalities. So although these circuits only have depth 10, and all the gates have a 99.99% of supposedly fidelity, the circuit fidelity is dramatically low. So there is something in between claiming a gate fidelity and claiming a circuit fidelity, okay? Which has to do with the crosstalk of the qubits, how they interfere one with the other. So how you can protect them. All these examples are done with superconducting qubits, okay? All of them. Would you get better numbers with ions? Yes, ions come out better. So you have a better result if you work with ion traps. Now, in order to do real progress, the community is starting to understand a number of things. that, sorry, this is you, no? Not me. The community is understanding that on top of defining our secrets through a process of characterization and calibration, when we go out to the public or to other colleagues, we have to do a severe benchmarking, which is not existing nowadays. There is no accepted way of doing the benchmarking of a chip. There is thing which is randomized benchmarking that we are doing nowadays, but this is not enough to define it. It only gives you averages of the quality of your gates. We need to go deeper into how you define the quality of a chip. And finally, we also need validation and certification. Okay? So we need eventually to certify a chip, which is not there. On the other hand, nobody is mentioning that, but for quantum computing being meaningful, you need cloud access, and that implies a lot of cybersecurity, okay, with it, because if finally your quantum computer is attacked by whoever, then it's useless. So we need a lot of work on the cloud access. A lot has been done, by the way. We need federated computing. Those are ideas which are very nice. Blind computing, for instance, is a beautiful idea. It's a classical idea that has a counterpart in quantum computers, which is, I want to do a quantum computation. You have a quantum computer, but I don't want you to know what you are computing for me. So can I disguise my problem in a way that you execute it in your quantum computer, I get the result, and I solve my problem, but you don't know what you solved? And the answer is yes, there is a way to do that. This is blind computing, okay? Are there schemes? We have schemes, but that will have to be put in place in the future. And definitely quantum internet. As you know, there are efforts around. There is an initiative in Europe to have progress in quantum internet, which depends on physics. Again, quantum repeaters is a problem of physics. So all these things are showing that at some point you may see a separation between the people that produce quantum computers and the people that benchmark, certify them. And we are starting to do this step. So in TII, we are building a characterization facility, and as of the end of this year, we will be characterizing chips from 5 different vendors. Let me move little by little to more theoretical aspects. Everybody says, well, quantum computers are good because you have a huge Hilbert space. Well, indeed, the official standard argument is that in n qubits you can store 2 times 2 to the n minus 2 real numbers. And this is certainly true. I mean, the characterization of a ket needs this amount of numbers. So vice versa. If I manage to put all these numbers in a state, I'm doing an amazing compression. Okay? I only have n elements, n physical elements. I have 2 to the n real numbers. The numbers go that 53 qubits, which is, as you know, where people claim that there is quantum advantage, is a petabyte. 1,000 qubits is 10 to the 282 exabytes. So it's ridiculous. But nobody says, and indeed it is certainly true that if you manage that, any processing is done in parallel. So if you have a superposition, it's done in parallel. That's quantum mechanics. What people don't say is that there is an issue about upload of this information. How do you upload all this data into quantum state? How do you read out? It's probabilistic, the readout. So that means that it is not true that a quantum computer will accelerate any computation. It's by far not true, okay? In particular, it may be helpful if the way you encode problems is very compact and the solution to a problem is very compact. In the middle, you may use the Hilbert space, but the upload and retrieval of information should be very compact. That's exactly what happens with Shor's algorithm. You give only n bits, you end up reading the period, n bits. In the middle, you develop a lot of entanglement, but you only need to upload and to retrieve a logarithmic number, okay, of bits. This is not true when people think that you may deal with, the clients of a bank on the millions, because then you need classically to upload all this information. So there is an issue of uploading information. I'm not saying that there are no other ways. I will give you an example which is very peculiar. Can I upload very fast a picture in a quantum computer? Well, formally, Seth Lloyd produced this example. Said, okay, my picture is in a CD, which are mirrors. So I simply say light, it bounces back, carries the information of the picture, and I capture with in guides. So I've uploaded in one go a lot of information. So there is no obstruction. But as a matter of fact, we have never been able to upload a large amount of information in one go so far. Okay? So this is one of the big issues. Now, let me refine a little bit what I said about classical improvements in the last years. And this is a very nice one. So of course, you can simulate quantum mechanics in an exact way. You simply write the ket, and that's it. This is limited to around 50 qubits. Okay? There was an effort for this competition that Google made in 2019, and you may know that it was done in Jülich, and they got up to 50 qubits with 3 months of computation or something like that. Limit is 50 qubits, okay, 52, 54, no more than that. Exact, okay, exact simulation. You can do Monte Carlo, but as you know, Monte Carlo suffers the problem of the sign problem. You cannot attack problems where you have frustration, genuine frustration. If you analyze critical systems in condensed matter, you find the critical slowing down of all these, the correlation between the configurations. You have to kill that. And they're very difficult to analyze problems which are not just an average. So time evolution, very difficult. Tensor networks came up as a solution to all these problems. It has no sign problem. It adapts to entanglement. It adapts to the geometry of the physical system and hence the many names of matrix state, projected entangled pairs of multi-scale renormalization ansatz, which are common names for these tensor networks. There are very nice libraries being developed. It has fantastic applications for finance and for chemistry that have been proven, and definitely have subtleties, like I mentioned before, the synergy with the quantum, with the Fourier transform. I'm using quantum, but it's a classical Fourier transform. So what is the idea in one go, just for you to know what's going on? Well, if you are strict that you want an exact representation of a ket, you have to deliver all these 2 to the n complex numbers. The idea of a tensor network is very, very deep. Can you represent this tensor as a product of tensors? If so, it turns out that each of these tensors has a dimension, is a matrix, has a dimension chi. So the counting of degrees of freedom is 2 to the n here versus n times, because there are n matrix, 2 to the chi square, which are the coefficients, and the qubit, the physical index is 2. So formally, you reduce any ket to this amount of degrees of freedom. So if I want a better representation, I simply need to increase this chi. This goes increasing, and I have a much better representation of the state. So it's adaptative. This chi can be proven to relate to the entanglement of the system. If it is a product state, chi is 1. If you have maximal entanglement, chi is 2 to the n halves. if you want to manage in an efficient way, you can handle up to polynomial number of n for chi. This has been used now very extensively. There is, if you check the literature, there's an explosion of people working on this, because you can try to revisit the simulations of condensed matter, and you can now really revisit even quantum computation. The pictures that you will see if you go to talks by these people are all how they set up the tensor network that describe your system. So really you have to go to your system, see if you have a honeycomb lattice, if you have a square lattice, if you have whatever, and you adapt your tensor network, and then you go through that. And just to give you an example, I think it's a funny way. Take a picture. Let me show you how I can handle a classical problem with a tensor network. I take a picture, dividing quadrants. Each quadrant is a quadrit, 1, 2, 3, 4. The first quadrant I divide in 4 quadrants, and so on. So my I index is labeling the address of the quadrant, and finally, C is the level of gray. So actually, this is a very simple way of seeing that 4 to the n numbers can be put in a ket of n quadrit. So you see this amazing compression. And next, what you can do, for instance, is to take C and represent as a product, as a tensor network. And as you increase chi, you have a much better representation. If you go lower chi, you're having a approximation to the picture. And you can see this is absolutely competitive against JPEG, for instance. Okay. But what's going really on nowadays, it's an effort called variational quantum algorithms. And it's really an interesting idea. So what is a quantum secret? A quantum secret is nothing else but a global unitary. So it's something that will take you from one point in the Hilbert space to another point in the Hilbert space. What you hope is that this this quantum secret will take you very near where you find the solution to your problem. But this is it. A quantum secret is a combination of gates. So how do we find a quantum secret that solves my problem? Well, there is a solution, hopefully. And this is, call it V. V is the one unitary that would solve your problem. And the question is, can I do it with a secret? And if I can, how many gates I need? And this is a wonderful theorem by Solovay and Kitaev that says that the increase in the number of elements in your secret is very moderate. So this is an existent theorem. It is not a construction theorem. It's not telling you which is the secret that solves your problem. It is telling you that at the most fundamental level, you can prove that there is a quantum secret that solves the problem for you quite efficiently. So there is hope. Huh? We have some mathematical step that tell us that there is such a thing as a secret that solves the problem. I think it's a very profound theorem. Actually, the proof of this theorem is so highly non-trivial in that it's never taught in any course. Okay? It's very, very difficult. So, hence the idea, okay, there is such a secret, but I don't know how to construct it. So I will do the following. And this was the idea by all these people from IBM. Let's make a secret which is random. Random. But with parameters that I can adjust. For instance, if there is a rotation, the rotation of a qubit is adjustable. And I play with that. Can I do a cycle where I start with a random secret, I read whatever I want the solution, doesn't work, and I feed back machine learning, and I change the secret. And I keep working in a cycle. So I applied machine learning to defining the secret. And they did that, and this was the first time that molecules were attacked, the first paper on quantum chemistry done by the IBM group a few years ago, and they attack all these molecules. Okay, was the first time that with a quantum device, people got a number for these things. This can be now understood much better, and to do that, let me take a trivial example. I want to do a quantum circuit which is only 1 qubit, and my gates are here, and I want to classify data that I put here as X. Can I classify by training these alphas? And indeed, you can see that depending on the number of these guys, I classify anything. So we see that we can build quantum classifiers, we can build any circuit that does the task that you want. Why this is possible, let me just mention, and this is an experiment to do that, because what you can see is that in this structure, what you are doing is playing with these alphas variationally, and when you expand all that, you see this is a Fourier expansion. So actually, all these gates, when you concatenate them, what you see is that your parameters are just defining coefficients of Fourier expansion. And this is the fundamental theorem, no? That Fourier expansions reproduce any functionality point to point, okay? And this is an experiment that shows that 1 qubit is a universal approximant. So to be very, very, very precise, 1 qubit plus real loading of k gates is as powerful as a neural network with an intermediate layer of k neurons. And both are equivalent to Fourier expansion. And this is what we call expressibility. Your circuit has this expressibility. But for condensed matter, things require more qubits. And nobody knows really what is the optimal way of doing that, how to encode the data, how to process, how to read out. The common and standard procedure is to make quantum circuits that are ordered by layers in this way. Every qubit can be transformed. There are interactions between the qubits, and you make layers. And as you increase the number of layers, you increase the precision. And this is the solution to this problem. In particular, this is a simulation of the Ising model, how to find the ground state. Here is the depth of the circuit in vertical. Horizontal is the precision. In log 1 over epsilon, epsilon being the error, so 10 to the 10 precision, 1 part in 10 to the 10 precision here. And indeed, as you increase the number of layers, you get a better simulation of your quantum system with a variational quantum eigensolver. So this is the idea. We are now doing the first efforts to go to 2 dimensions. So of course, people are starting to work with condensed matter standard systems. Hubble model is waiting for us in the future, okay? So we are preparing the circuits for the 25 qubit machine, and we will try to use variational quantum eigensolvers to attack condensed matter systems of 2 dimensions, which is that's one of the spirits of the quantum computers. I think, I don't know what time I should finish. Say that again? I can go? Oh, okay. No, I only have one more item. Either I take it out or not. I just wanted to add one item that may sound so strange to everybody. Everybody says quantum computers are faster than the classical computers. They can attack problems that nobody can attack, and so on. Well, I think there is an issue which is overlooked by everybody. Quantum computers may not be faster than classical computers, but they may be energetically more efficient. So I will give a number. The supercomputing, our supercomputer in Barcelona spends 1.5 million euros in electricity. This is my Nostrum 4. My Nostrum 5 will spend a total of 100 millions in maintenance for 4 years. 100 million, maintaining the classical computer. And the reason is electricity, okay? Chilling the machine and computing. So far, 1/3 chilling, 2/3 computing. Well, why not thinking whether quantum may be a solution to energy? Okay, that's the idea. And it's a very naive idea, but I will use an example. And this is an example that makes sense because you may know that the energy on the planet, humans use less than half. The other half is used for computing services, not for heat or for transportation. So computing is taking an enormous amount of energy in the planet. One of the many things which are being done systematically, besides Bitcoins, okay, that take a large percentage, is this thing, is checking the risk of portfolios. And as you know, every bank has a place where they spend hours and hours there computing for every client the risk. It's a very repetitive computation that has to be done systematically because the market is changing, okay? Simplification of the kind of things that you do is option pricing. So the idea is that S is the value of a stock, and you have it as time t, and you want to know at time much larger, capital T, maturity time, and I want to predict what is my expectation of making money. So if the value at the maturity time is bigger than a threshold, I call it strike, I will make money. If not, I lose it. So I have to compute this thing. The probability of that the value is ST times ST, and that will be my profit, okay? If not, I'm losing. I take the average. So what people do is that they simulate the evolution of this stock with a Black-Scholes equation, no? They think that there is an interest rate that will force an increase, but there is a stochastic variable and a volatility associated to that. And then that's it. Because there is a stochastic element here, what people do is a Monte Carlo. So they make trajectories towards the future, and these trajectories spread little by little, related to the volatility. And you end up here, and now you have to collect those that are on top of a value and discard the others, and that would be the way you compute your return. So this is a more realistic thing, 10,000 paths, and how people compute this. That takes a lot of effort. You don't have an asset, you have many assets, and they are correlated. So the evolution is not that simple, it's a correlated evolution. So what about making that, like that, making a photon that enters waveguides and can jump just like this, and finally you get the probability distribution. And then I collect the light. So does it make sense? Can I make a circuit where I do amplitude distribution, compute the expected payoff, and even if it is quantum, I can do amplitude amplification. Grover's algorithm apply here. And indeed, you can do the gates to generate the amplitude. You can compute everything. And you can design now the chip. And here are the pieces. They are going down and down till you make them very precise. And we did it. Okay, so at the NTU, part of CQT and our team did the chip that computed this thing. A single photon enters. Those are the generator of single photons. It's probabilistic, so you try to get one photon at a time. Those is the module that computes everything, and you have single photon detectors in the very end. And as you see, foundries are part of our teams, okay? And this is a match between the expected probabilities and the real ones, and as you see, well, of course, physics obeys the laws that they have to obey. So it fits exactly what we wanted. The error goes to zero, and everything is good. And you can even say, okay, now you have the differential equation, but if not, you can train any probability distribution by the technique of generative adversarial networks. So you make two elements, one generates probabilities, the other discriminates. That's how you recognize faces, how you generate content nowadays. It's a standard technique, and we did that. So we train the circuit. This chip is trainable, okay, against the neural network that was discriminating. And it works, and the results are as you expect, the real distribution versus the one. So we have a chip that learns any probability distribution. It bypasses Monte Carlo, and then it computes at the speed of light. And there is no need that this is done with single photons. It can be done with light. So there is an effort in Singapore to take these kind of ideas a step further, which is think of the problem you want to solve and adapt what we know, the elements we have from quantum mechanics, to find a solution which is energetically better. Not faster, energetically better. Okay? So we are building two plants, actually. One plant putting together everybody, and then a particular action separate, and we're involving the foundries and all the teams to see if we can do these kind of things. I think this is the future. A piece of the future of integrated photonics. I'm not saying this is the future for everything, but keep in mind, quantum advantage may be quantum advantage in energy, not in speed. Okay? Challenges. Well, look, this is my last transparency. I've fought with many of my colleagues that say that quantum computing is a matter of engineering. I disagree completely, okay? I disagree. I think it's a matter of physics. Since the last, I don't know for how many years, there has been no dramatic improvement of the coherence time in our devices. In none of the, not in ions, not in superconducting currents. So the depth of the circuits are exactly as they were, okay? Now, if the depth is what it is, imagine you want to do a variational quantum eigensolver. In order to entangle pieces, qubits in your chip, you need layers. If you don't have depth, you cannot even entangle your qubits. So actually, we are building, at this moment, universal incoherent machines. So we are building incoherent D-waves, but they are universal. So there is an absolute need, okay, in improving the physical properties of our system. So as you know, so for instance, a lot has to do with fabrication. So Abu Dhabi is a new place, so we made a clean room that we are not doing any other thing to avoid cross-contamination. In Singapore, we had a clean room. It got cross-contaminated. It's a mess. We have to replace the evaporator. So, and that's an expensive, and in particular, delay in time. You know that there are many people, the guy, you know, Quantware, he's obsessed with analyzing niobium, tantalum. This is a chip that we are doing at CQT, 10 qubits. Now, all the connections are being changed to indium, okay? And so on. So every day, there is a progress to improve these things. Yet, there is no way, I mean, in average, all the chips have coherence times of less than 40 microseconds in general. There is a well, as you know, Nakamura was the guy who first made this qubit in '99. He himself has reached 400 microseconds, but in the chip he's producing, out of 64 qubits, it's less than 50 work. It's not on, the yield is, they don't even have a chip that works all together. So it's extremely difficult, okay? So if we don't fight the coherence, there is no meaning in the number of qubits. If we don't find the crosstalk or any other source for the secret fidelity, there is no meaning. And if we don't manage a relevant scaling, there is no meaning to call in all these quantum computing. You know, there are really experiments which are very peculiar, like the cosmic rays. Okay, cosmic rays now apparently, well, they break the Cooper pairs, and you're done. Okay, so there are not that many, But if we go to larger systems, that it will be an obvious source of problems. Okay? So we are conducting another experiment in the mountains of the Pyrenees down to analyze in detail the effect of cosmic rays in this. Okay, I think this is everything I wanted to say.
Thank you.
Thank you. That was a great talk, from saying that quantum computing is here to saying all the barriers. It was a very honest and clear talk, and I really appreciate it, not to mention impressive. So I've been reading about neuromorphic computing, and I was extremely intrigued by the end when you talked about the energy, and that's why they're selling that. Are you working on that, or do you know of successful approaches?
Actually, the last member of CQT that has come is a woman, Alexia Ofrèvre from Grenoble, and she's only on that, and she's building on a manifesto along these lines for the planet, and there are many people joining, and yeah, it's one of the new lines of CQT is exactly this one.
But you're actually looking at possible devices for new
So there are two
materials?
things. One is the theory, so this is thermodynamics, quantum thermodynamics, let me call it like that. And the second is that we are trying to do an effort in photonics. Okay?
Thank you very much.
Yeah.
Please.
Yeah, they're coming.
Thanks, very nice talk. Just a quick question. You mentioned right at the beginning there is a tension, or let's say competition between two contrasting requirements, having non-coherence and interacting. And now, in your view, it seems that ions are the best, let's say, for this kind of, for fulfilling this condition. But now, if it is so, why there are still people using other, let's say, technologies?
Yeah, let me be super honest. I had to choose the platform in Abu Dhabi, and I chose superconducting currents, okay? Because although at present ions produce better fidelities and better results, and they have very, very many nice things, they are limited in size, okay? So to be more precise, IonQ, Chris Monroe, probably you know, Maryland, what he is doing now is a chip of 23, but the next is 32 qubits that they can talk to each other, and as I said, many at a time. In 18 months, he's promising to sell machines, no cloud access, sell, okay? That would be the following. There would be machines of 32 qubits, and they will define 32 as the block size of the number of qubits, and then another 32, whatever number of 32s, controlled separately. And now they can move them, you know, this was an experiment many years ago, they can move them, talk, and take them away. And from then on, you can do whatever swap, okay? So the idea is, in ions, they are levitating, they are 32, and on the chip, you move them, you approximate, you take them away. On top, you have to read them. And read out is very difficult. On top, it has to work forever because you're serving the community. They claim that they will be able to upload the ions in 1 minute, and they will sustain the performance for a month. That's a claim in 18 months. Technical, and he claims, is one of the guys who says, this is engineering. I do have my doubts. Now, on superconducting qubits, we have a lot of challenges, and you guys know better than me, okay? We should maintain these superconducting currents, no matter all the things which are going into them. And we have to keep them on the tight control. The big problem is that they are very sensitive to magnetic fields, and immediately you have crosstalk, immediately. There have been ideas which are very clever, like making 2 qubits and putting a 3rd qubit, which is dumb, but it makes a quantum barrier between them. I love this kind of idea. It's so different. So that's the idea of Google. Okay, you know they put 54 qubits. One didn't work, but there were 54. There were 80 qubits separating the other, pushing down the crosstalk. There are other ideas, like also IBM, of annealing, they call it annealing, burning the Josephson junctions so that they are better and homogeneous. You need homogeneity. But when I look at superconducting currents, I see continuous progress myself. And they scale well. Then you can scale, okay? It's my bet. There are other people, and I know other people that are with big pockets. They believe that the solution will be photons. Photons do not interact. So this idea of psi-quantum, of making a state, which is a cluster state, probabilistically, but then you know exactly who is entangled with whom, and now do a series of operations which are measurements, and this is the one-way computer philosophy that was many years ago. They claim that this is the way to go. As a matter of fact, there has been 0 papers proving that. I understand it's secret. And they claim that they will only come public when they have 1 million qubits. What can I say? I mean, look, it's like playing poker here all the time, no? I mean, I'm familiar with MV centers. I don't think they will get anywhere in the short time. I think they are fantastic sensors. Cavities, I think they are creating cut states as qubits. Wow, making an interaction between 2 cut states is really a mess, really a mess. I appreciate a lot what is going on in neutral atoms, because as you know, with tweezers now, they can do anything. They can move them, put them here, put them there. We have in our team, Huan Chan, she was in one of the lectures. Huan Chan has managed to have hundreds of atoms, and she has drawn the Merlion, which is the symbol of Singapore, with tweezers. I mean, wow, that's impressive. Yet, interactions on the control, we have not gotten any. It's a complicated situation, and you're putting a lot of money, a lot of money, you know, just buying the fridges and the electronics. I just counted, if you are, the cost nowadays of a machine per qubit is $30,000. 30. So if you go to 60, it's 1.8 million. Given that you have already a lab and you have everything, okay? Just the cost of going for that chip. So it's heavy. Yeah? Yeah.
I mean, it seems to me that as electrical engineer, I can recognize that, practically speaking, implementation of Scholl algorithm is a kind of a dream, but not exactly implementable. So from that point of view, we always see that we have to face small quantum chips embedded among massive classical chips. Mm-hmm. And looking into that, so then we need to partly give up orthodox approach to a quantum computation, right? And we can think about hybrid solutions. And could you see, for example, combination of rapid single quantum flux electronics as implementing classical chip, plus interface with flux superconducting qubit or with transform qubit as a solution?
Yeah, you are fully right. So Shor's algorithm is far in the future. Therefore, and now we work tomorrow to do what? Okay, so let's forget Shor. So this was the name of NISQ era, the near intermediate noisy computers, no? Noisy intermediate quantum computers that Preskill put forward. In the NISQ, there is a fundamental idea, which is with the few qubits you have, do a variational quantum algorithm. And this is massively done. What you are saying is I think, if I understand well, is a more subtle thing. Let's look at the problem, and let's try to combine everything we have. So this is, for instance, what a company called Horizon is doing. They take your problem, they look at your problem in detail, and they see what are the bottlenecks. And only in that bottleneck, they accelerate it. So they make very small calls. But hopefully, this is enough to accelerate the whole thing. And this, as I said, is a big, they got $12 million, just people that do that on a software piece. I see this coming more and more, and the fact that now quantum computers will be in the supercomputing centers, I will see this more and more. Okay? How far you can combine the two things. Many people say that the quantum computer will be only a QPU. You will have CPUs, GPUs, you have TPUs for tensor product units, and you will have QPUs. But the real thing will be done centrally and only making selective calls. And I agree with this philosophy. I think it's the future, yeah. Meromorphic was also mentioned, no? So now the future of supercomputers is not a unique solid thing. It's an extremely diverse machine, okay? That depending on the problem acts in a different way. So I think there is a lot of thinking in the HPC community how to integrate quantum inside. There is another piece which I didn't mention, which is cybersecurity. Cybersecurity is critical for every country. Quantum is essential there. And you may see protocols added to classical computation to authenticate, or to share a key. So you may see mixings which are unexpected as of now. Well, you may have distributed computation nowadays. You may add layers of quantum to secure it. Again, so computing mixes with quantum, but in a different way for a different purpose. So it's quite a hectic moment, I would say.
Thank you.
Thank you. We are behind schedule. I know there are questions, but maybe we can continue. You can continue after the session. So we thank the speaker.
Okay.